Hey everyone, welcome back. Today we're going deep, really deep, into the world of black holes.
Sounds exciting.
It is, right? And to guide us through this cosmic journey, we have Jörg-Owe essay, Black Hole Simply Explained. Have you had a chance to look at it?
Yeah, I have. It's a really great starting point for anyone who wants to get a handle on these, frankly, mind-boggling objects.
Totally agree. Schneepat really breaks it down in a way that's, I think, accessible,
Absolutely. And he doesn't shy away from the complexity either, which I appreciate.
Yeah, for sure. So before we get too far, let's start with the basics. What is a black hole, according to Schneepat?
Well, Schneepat defines a black hole as a region in space-time.
Okay, space-time.
Yeah, where gravity is so strong that nothing, not even light, can escape.
Whoa, okay, so it's like super strong gravity.
You could say that it's like a cosmic drain where gravity's pull is just so intense it warps like the fabric of reality.
It warps the fabric of reality. That's intense.
It is.
But how does something like that even form? Is it like a giant vacuum cleaner just sucking things up?
Not exactly. Schneepat explains that black holes are actually born from the death throes of massive stars much bigger than our own sun.
Ah, okay. So when these stars die.
Right, they run out of fuel and then they collapse under their own, immense gravity.
So like a balloon suddenly deflating?
Kind of, but on a much grander, more violent scale.
Okay, so it's a pretty dramatic event.
Oh, absolutely. Schneepat calls it a supernova explosion. It's this catastrophic implosion that can actually give rise to a black hole.
So the star implodes, but it doesn't just vanish, right? What's left behind?
Well, what's left behind is the star's core, but it gets crushed into this infinitely dense point.
Infinitely dense.
Yeah, Schneepat calls it a singularity.
Singularity.
Mm-hmm. It's mind-boggling to think about. All that matter squeezed into an infinitesimally small space.
So all that's left is this tiny point of infinite density.
It's at the heart of the black hole, yeah. But it's surrounded by what's called the event horizon.
Event horizon.
This is the point of no return.
Okay, point of no return.
Anything that crosses the event horizon is pulled into the singularity and can't escape.
No escape.
Nope, not even light, which is why we call them black holes.
I see. So once you cross that line, you're basically toast. No coming back.
Exactly.
Wow. This is where my brain starts to melt a little.
I know what you mean. It's pretty heavy stuff.
So Schneepat mentions that not all black holes are the same. He talks about different types, right?
Right. He outlines three main categories.
Okay, let's hear it.
We have stellar black holes.
Color.
Then there's intermediate black holes.
Intermediate.
And the big ones, supermassive black holes.
Supermassive black holes. Okay, so three different types. What makes each one different?
Well, Schneepat explains that stellar black holes, those are the most common. They form from the collapse of individual massive stars. They're usually a few times more massive than our sun.
Okay, a few times bigger than our sun. That's still pretty massive.
It is. Then you have the intermediate black holes.
The in-betweeners.
Yeah. Their formation is still a bit of a mystery, but some scientists think they might come from mergers of smaller black holes.
Oh, interesting. So they're like combining to become bigger.
Exactly.
And finally, the supermassive black holes. These sound like the real heavy hitters.
They are. Schneepat says they are found at the centers of galaxies.
Including ours?
Including ours. They can be billions of times more massive than our sun.
Billions. That's just inconceivable.
It's hard to wrap your head around.
And Schneepat mentions that our galaxy's central black hole actually has a name, right?
Yes. It's called Sagittarius.
Sagittarius A. So we're like dancing around a supermassive black hole right now. That's both terrifying and awesome.
Definitely awe-inspiring.
But we've got these different types, but what about their features? Like, what makes them tick?
Well, Schneepat dives into some key properties that all black holes share, regardless of size. Things like mass, spin, and something called accretion disks.
Okay, mass seems pretty straightforward. The more massive the black hole, the stronger its pull.
Precisely.
Yeah.
But Schneepat points out that spin adds another layer of complexity.
Spin. Like, they're spinning.
Yeah. A spinning black hole can actually drag space-time around with it.
Hold on, space-time. Like the fabric of reality we were talking about.
Exactly. So it's not just gravity that's warped, it's the very structure of the universe.
Okay, my brain officially needs a break.
Yeah.
All right, so my brain is still recovering from that last bit. But I have a question. If black holes are, well, black, How do we even know they're there? How do we find something that doesn't emit light?
It's a great question, and Schneppat actually addresses it in his essay. He explains that even though we can't see black holes directly, we can observe the effects they have on their surroundings.
So it's like we can't see the wind, but we can see the leaves rustling.
Exactly. Like, Schneppat describes how astronomers can detect black holes by observing the gravitational influence they have on nearby stars.
So if a star is acting a little funky, orbiting an empty spot in space, that could be a sign of a black hole.
Exactly. Like, if a star is orbiting something invisible, but incredibly massive, it's a pretty good bet there's a black hole there.
That's pretty clever. It's like deducing something unseen by how it affects the things we can see.
Right. It's a testament to the power of, scientific observation and deduction.
And what about those accretion disks, the swirling gas and dust that we were talking about earlier?
Right. Schneppat points out that those accretion disks, they emit powerful X-rays as they spiral into the black hole, and we can detect those.
So even though the black hole itself is invisible, this swirling disk around it gives off a signal we can pick up.
Exactly. And Schneppat also talks about something even more mind-boggling: gravitational waves.
Okay, gravitational waves. Those are kind of a big deal, right?
They are. Schneppat explains that Einstein's theory of general relativity predicted that massive objects like black holes create ripples in the fabric of space-time.
Ripples in space-time. So, like, the universe itself is being stretched and compressed as these black holes move around.
Exactly. And these ripples, these gravitational waves, they can travel across vast distances.
Wow. And we can actually detect these ripples here on Earth.
Yes. Schneppat mentions that scientists have built incredibly sensitive instruments that can pick up these tiny distortions in space-time.
So we're essentially listening to the echoes of cosmic events, maybe even billions of years old.
It's pretty amazing when you think about it.
It is. But I think it's also important to remember that there are a lot of misconceptions about black holes.
Yeah.
A lot of that comes from science fiction and pop culture.
Yeah, definitely. Schneppat touches on some of these myths, like the idea that black holes are these cosmic vacuum cleaners sucking up everything in their path.
Right, like giant monsters gobbling up everything in sight.
Yeah. But Schneppat clarifies that black holes have gravitational pull just like any other object with mass. It's just that, their pull is incredibly strong because they're so dense.
So you're saying that if our sun suddenly collapsed into a black hole, the Earth wouldn't just get sucked in?
Right. The Earth would continue to orbit the black hole just like it orbits the sun now. The mass would be the same, so the gravitational pull wouldn't change.
Okay, that's somewhat reassuring. But I gotta admit, black holes still seem pretty mysterious and, dangerous.
They're awe-inspiring objects, and, there's still a lot we don't know about them. Schneppat himself acknowledges that black holes represent some of the most profound mysteries in the universe.
Like, we've only just begun to understand them.
Exactly. And yet we've come a long way. Like, Schneppat points out that the first image of a black hole captured just a few years ago was a huge breakthrough.
Yeah, that was big news. It wasn't just a theory anymore. We could actually see it.
And it wasn't just a blurry blob. We could see the shadow of the black hole against its accretion disk.
Like peering into the heart of darkness and seeing something incredible.
Exactly.
And I imagine that image has sparked even more research.
Oh, absolutely. It opened up all sorts of new avenues for investigation. Schneppat suggests that the future of black hole research is really exciting, with lots of discoveries yet to be made.
I can't wait to see what they find.
Yeah.
One thing that really caught my attention in Schneppat's essay was Hawking radiation.
Yeah, that's where things get really mind-bending.
Seriously. Because up until now, we've been talking about black holes as these inescapable objects, right? Nothing can escape. But Hawking radiation suggests that might not be entirely true.
Right. Schneppat explains that Stephen Hawking, the brilliant physicist, proposed that black holes aren't entirely black. He said that through some complicated quantum mechanics, black holes can actually emit particles.
Oh.
And as they do, they lose a little bit of mass and energy.
Hold on. So black holes can leak. Something can actually escape their gravitational pull.
In a way, yes. It's a very slow process, but over vast stretches of time, this Hawking radiation could cause a black hole to evaporate.
So even these seemingly eternal objects aren't immune to the passage of time.
It's a mind-boggling concept, and it has some pretty big implications for how we understand the universe. Schneppet admits there's still a lot we don't know about Hawking radiation, but it's a fascinating area of research.
It certainly raises a lot of questions, but that's what makes this whole topic so interesting. So we're nearing the end of our black hole deep dive with Jörg-Owe Schneppet's essay, Black Hole Simply Explained. We've talked about how they form, some of their, I guess you could say, weird properties.
Yeah.
And how we even know they're out there, even though, we can't see them.
Yeah, and we even talked about Hawking radiation, which is pretty wild. I mean, the idea that even black holes might not last forever.
Right. It's like what is forever in the universe,
Yeah.
But I wanted to touch on something else that Schneppet brings up. He talks about how those supermassive black holes, the ones at the centers of galaxies, they don't just sit there,
Right. They actually impact how the whole galaxy evolves.
Yeah. And Schneppet, he explains that their gravity is so strong, it can actually influence how stars form, I think.
Yeah, he talks about that and how they create these powerful jets of energy.
It's like they're shaping the whole galaxy.
Yeah, they're not just these, destructive monsters. They're kind of, I guess you could say, creative forces too.
It's amazing to think about how everything in the universe is connected. Yeah. Like how these massive objects could have such a big impact on everything around them.
It really is. And it makes you realize how much we still don't know.
Exactly. Speaking of things we don't know, are there like big unanswered questions about black holes that Schneppet hints at? Mysteries that, scientists are still trying to figure out.
Oh, absolutely. I mean, one of the biggest ones is the singularity itself. Like, what actually happens at that point of infinite density?
Yeah, good point. Like, do the laws of physics as we know them even work there?
Right. And then there's the question of information. Like, what happens to information that falls into a black hole? Is it gone forever?
That's a good question. Like, does it just disappear?
That's the information paradox. It's a real head scratcher.
And we can't forget about dark matter and dark energy.
Oh yeah, big mysteries there too.
Schneppet doesn't get into those too much, but they're kind of connected to black holes too, right?
Absolutely. It all ties into how the universe works.
I guess we're always going to have more questions than answers.
That's the beauty of it, right? There's always something new to discover.
Well said. So I want to say a big thank you to Jörg-Owe Schneppet. His essay, Black Hole Simply Explained. It's been a fantastic guide for us.
Yeah, it's a great resource for anyone who wants to learn more about black holes.
Definitely. And to everyone listening, thank you for joining us. I hope you learned something new.
Yeah, and maybe we even blew your mind a little bit.
That's the goal. We'll be back soon with another deep dive into some other fascinating topic. Until then, keep looking up.
And keep those questions coming.